Listen closely. This is a story about how the biggest idea in modern cosmology, an expanding universe, ended up with the wrong name for most of a century. It's not a conspiracy. It's messier than that. It's how data, theory, translation, timing, and reputation collided. And it begins before either name on the law shows up. At the start of the 1900s, astronomers still argued about what the spiral nebulae were. Were they newborn star systems inside the Milky Way, or island universes far beyond it? While that debate simmered, two quiet discoveries set the stage for everything that followed. First, Henrietta Leavitt, working at Harvard, discovered a tight relationship between the period and brightness of Cepheid variable stars. If you could measure a Cepheid's flicker cycle, you could calculate its true luminosity. Then compare that to how bright it looks to infer distance. That's a cosmic yardstick. Second, Vesto Melvin Slipher at Lowell Observatory spent long nights pushing a spectrograph to its limits. He measured the radial velocities of those spiral nebulae. Again and again, the spectral lines were shifted toward the red, receding, some with staggering speeds for the era. He didn't have good distances, but he had motion. By the late 1910s, the picture was confusing. Einstein, having just completed general relativity, applied his equations to the universe and didn't like the result. Gravity made it unstable. Everything collapsed. So he inserted a counterterm, the cosmological constant, to hold the cosmos static. Meanwhile, Alexander Friedmann, a Russian mathematician, did something unthinkable in 1922. He solved Einstein's equations without the stay-still bias and found dynamic universes. They could expand or contract. Few noticed. The idea was mathematically sound and physically unsettling. Now the key move. In 1927, a 32-year-old Belgian priest-physicist, Georges Lemaître, published a paper in French in a relatively obscure Belgian journal. He did three things in one shot. He took Einstein's general relativity seriously without the demand for a static universe. He built a simple, homogeneous, isotropic model in which space itself could stretch. And then he connected theory to observation. He took Slipher's recession velocities and the best available distances to those nebulae and showed a proportionality. Radial velocity equals a constant times distance, v hxd. He even estimated the constant, hundreds of kilometers per second per megaparsec, roughly 575 by his calculation. The point wasn't the exact number, it was the relation and what it implied. Space is not a stage, it's elastic. Distant galaxies aren't flying through a static void. The void itself is enlarging. That's the discovery. A modern law, wrapped in a model, anchored by data, but it was written in French. The journal had a small readership. The title did not scream revolution. Lemaître sent copies to major astronomers. Some read it, others filed it. Einstein reportedly dismissed it at first. Eddington, Lemaître's on and off mentor, was intrigued, but busy. The work existed, but it did not roar. 2 years later, 1929, Edwin Hubble, working at Mount Wilson with the 100-inch Hooker telescope, had something Lemaître didn't, a powerful public stage and a clean distance ladder powered by Cepheid variables he had identified in Andromeda and beyond. Hubble assembled the velocities, largely Slipher's measurements, and distances he derived, plotted them, and found a striking linear trend. Farther galaxies recede faster. The result was crisp, the graph unforgettable. The paper cited data sources, but did not highlight Lemaître's 1927 relation. The press took hold. Galaxies are fleeing. The universe expands. Names locked into public memory. Hubble, Mount Wilson, the Hooker telescope. The constant became Hubble's constant. The relation became Hubble's law. Pause here. What exactly did each man do? Lemaître, in 1927, derived the possibility of expansion from general relativity and married that to the observed redshifts, explicitly yielding v eon hxd with a numerical estimate. That's theory plus observation plus relation. Hubble, in 1929, produced a cleaner, more persuasive empirical correlation using better distances and a larger organized data set, and showed the relation with a now iconic plot. That's observation plus correlation plus publicity and institutional weight. Both depended on Slipher's spectra. Neither could do their work without Leavitt's yardstick. The difference was visibility and framing. Lemaître's article was a quiet thesis in a dim room. Hubble's paper threw open the curtains. Now, the twist that misled a generation. In 1931, at Eddington's suggestion, Lemaître's 1927 paper was translated into English for a major British journal. This should have fixed the visibility problem, but the published English translation omitted the section where Lemaître had calculated the constant from the data and the table of velocities and distances he used. It read like a theoretical note, rather than the theory observation synthesis it truly was. For decades, this omission looked like theft or suppression. Later correspondence made it clear. Lemaître himself had removed those parts, convinced the particular numbers were outdated and not worth reprinting. He didn't fight for priority. He cared about the physics moving forward. In the meantime, Hubble and his colleague, Milton Humason, were pushing into fainter galaxies, higher redshifts, and refining the trend, though their original distances made H look 5 to 7 times larger than what we accept today. As better calibrations arrived, the constant fell. The framework held. Einstein, after initially resisting, publicly endorsed expansion at a 1931 meeting, calling the cosmological constant unnecessary, "My greatest mistake," he later said, though his relationship with that term is more complicated than the quote suggests. Lemaître went further conceptually, proposing a primeval atom in 1931, a dense early state that later critics dubbed, somewhat derisively, the Big Bang. The label stuck, the sneer did not. Why did credit skew for so long? Several forces pulled in the same direction. Language and venue, French in a local journal versus English in a widely read American outlet. Data curation, Hubble had a branded, growing catalogue and a sensational plot. Institutional prestige, Mount Wilson was the cutting-edge machine shop of the sky. Personality, Lemaître was not a self-promoter. Hubble understood the value of headlines. And the translation, by stripping the numerical VD section, the paper most English readers encountered from Lemaître looked like pure theory, conveniently leaving the empirical first to Hubble. Pull back and see the whole machine. Leavitt built the yardstick. Slipher recorded the recessions. Friedmann opened the equations. Lemaître connected the dots and wrote down the law and a value. Hubble sold it to the world with a plot everyone could understand. Humason extended the line. Eddington mediated. Einstein surrendered the static picture. That's the chain. This isn't just housekeeping. Who gets named on a law shapes who students learn about, who history's center, who appears on lecture slides, and who falls out of sight. For most of the 20th century, we taught Hubble's law as if one man looked and the universe confessed. Only in the early 21st century did the community formally revisit the name and adopt the Hubble-Lemaître law. The change doesn't erase Hubble. It restores the missing page. Let's get concrete about the law itself. A galaxy's observed redshift, how much its spectral lines slide toward longer wavelengths, can be translated into a recession velocity for nearby objects, where relativity simplifies. Plot that against independently measured distance, and you get an approximately straight line. The slope is the Hubble constant, h0. The units are odd at first glance, kilometers per second per megaparsec, because it's a rate of expansion per unit distance. Interpret it this way, each megaparsec of separation adds that many kilometers per second of recession. Double the distance, double the recession speed. This isn't Doppler motion through space. It's the metric of space itself stretching. Locally, gravity can bind systems. Galaxies don't rip apart. The solar system doesn't dilate. On large scales, the average flow dominates. The first values for H were around 500 to 600 km Sasuj MPC because the Cepheid calibrations were off. As distance scales were corrected, the number fell, eventually landing in the neighborhood of Marshish 70 km MPC. Today, measuring H0 precisely has become its own mystery. One method, building out the cosmic distance ladder with Cepheids and supernovae, yields a higher value. Another, inferring it from the early universe's imprint in the cosmic microwave background, yields a lower one. This Hubble tension is a modern echo of the old story. Your measurement depends on your model. Your model depends on what you trust in your chain of inference. That's not a failure, it's physics telling us where to look harder. But the essential insight does not wobble. The universe expands. The tie between velocity and distance is linear to first order. That means the observable universe has a finite age. If you rewind the film, distances shrink until matter and radiation occupied much denser states. Lemaître's primeval atom was a poet's way of saying what our modern LCDM model computes with parameters. A hot, dense early epoch, cooling and diluting over billions of years, forming structure along the way. Now look again at the human element. Slipher measured the first redshift of Andromeda? No. Andromeda's is actually blue-shifted, one of the rare nearby cases moving toward us. Most of the other spirals he measured were redshifted, racing away. His work took painstaking patience and was not glamorous. Yet without his velocities, there is no line to draw. Leavitt, working from photographic plates of the Magellanic Clouds, extracted the period luminosity law that made all of this measurable. For decades, she did not get full recognition. Without her relation, there is no distance scale. Friedmann, a mathematician far from the centers of astronomical power, showed that Einstein's equations did not require the universe to sit still. He didn't live to see the idea vindicated. He died in 1925. Without his openness to dynamic solutions, there is no theoretical frame. Lemaître, bridging priesthood and physics, did the synthesis. He didn't only imagine expansion, he reflected it in a model and tested it against data. He computed a constant. He wrote down the linear law. Hubble, with privileged access to the best telescope and a rigorous program, produced a compelling empirical plot and gave the public a simple message. He also understood the value of naming. In hindsight, he gave modest credit to Slipher, but his brand overshadowed the chain. Humason, a former mule driver who became an astronomer, was Hubble's partner in pushing spectra to dimmer and more distant galaxies. He turned hard nights into data points that extended the law. Eddington saw, connected, and translated, sometimes literally. Einstein changed his mind publicly, and that mattered. Institutions amplified the message they were ready to hear. That's what Hubble-Lemaître means now. It is a hyphen that encodes the bridge between theory and observation, between a derivation in a Belgian journal and a plot from a mountaintop. It reminds us that science is not only correct ideas, it is also who writes them, where they appear, who reads them, and who advocates for them. There's one more layer. Consider why a linear relation is so persuasive. In a chaos of numbers, a straight line calms the mind. It suggests a simple principle is at work. But a straight line also invites overconfidence. Early H values were wrong by a big factor. The law still stood. That's a deeper lesson. You can be right about the structure and wrong about the scale. You can have the relation before you have the calibration. Lemaître had the relation. Hubble had the demonstration. The name should have reflected both from the start. So what do we learn beyond restoring a line of credit? First, the way we publish matters. Language barriers and journal reach aren't side notes, they shape history. Second, theory without data doesn't win. Data without theory doesn't explain. The winners are the bridges. Third, humility can hide you. Lemaître's choice to strip his own numbers in translation was intellectually honest and strategically disastrous for his priority. Fourth, the past is not fixed. Communities can correct the record without tearing down the achievement. Renaming the law did not diminish Hubble, it illuminated Lemaître. When you hear the universe is expanding, don't picture galaxies shooting through a static void. Picture the grid itself stretching, carrying galaxies with it. The way dots on a balloon separate as the balloon inflates. And when you hear Hubble's law, let your mind auto-correct Hubble Lemaître. Then keep correcting Leavitt, Slipher, Friedmann, Lemaître, Hubble Humason. The straight line on that plot is a team photo. We tend to tell science as a string of lone genius moments. That's not how it happens. It's a relay. The baton is a skeptical method and a record of who passed what to whom. If you want to see the real engine of discovery, look at the handoffs. Here's the clean summary you can carry out of this episode. The relation Scheele with HXD was first derived and numerically estimated by Georges Lemaître in 1927, combining general relativity with observed redshifts. Edwin Hubble's 1929 paper provided a powerful empirical plot, using better distances and widely publicized the expansion, cementing the idea in the public and professional imagination. V.M. Slipher's earlier spectroscopy supplied the crucial recession velocities. Henrietta Leavitt's Cepheid law supplied the distance scale. Alexander Friedmann's solutions supplied the theoretical possibility. A 1931 English translation of Lemaître's paper omitted his numerical result and data table, cut by Lemaître himself, which obscured his priority for decades. The modern community now uses Hubble-Lemaître law to reflect the combined achievement. That's the lost page, not a correction to the physics, but a repair to the story we tell about it. When we repair the story, we also sharpen the science, because we see all the pieces that had to interlock before a straight line could appear on a plot. If you grasp that, you're ready for what comes next. The strange afterlife of that straight line. How a background whisper discovered by accident in the 1960s confirmed the expanding picture. And how today's precise measurements of the slope are arguing with each other in ways that might be telling us something new.